Hello and welcome back to my channel. In the last video we talked about using LP to model bipartite graph or bipartite matching, and just like a recap, we talked about how it's a 0-1 LP problem, and 0-1 LP problems are hard, so to solve them we would have to relax the 0-1 condition. In this video, we are going to talk about how to use LP to model vertex covers. We want to use LP for modeling vertex covers. So the first thing we want to talk about is what vertex covers are. So given a graph, let's say we are given a graph. With vertices and edges. We need to find, for a vertex cover, we need to find a minimum size subset of vertices that cover all edges. So we need to find a minimum sized subset of vertices that cover all edges. So what does this mean? Let's illustrate this with a simple diagram. Consider this diagram where this is a vertex, this is another vertex, and this is an edge. So you have from this to this to this, you have another connection here, you have another connection here, and you have these edges. And we want to find its vertex cover. That means we want to find a minimum size subset of vertices that cover all edges. So this is what we can do. If we choose, let's say we choose this, we choose all vertices. It covers all edges correctly, but can't we choose a lesser number of vertices that can also cover all edges? So we can start from here. This edge, we can say this edge and this edge, let's say it's covered by this one. So we've chosen this, and these two edges are covered. This edge and this edge, let's say they are covered by this one, and that means this and this are covered. And let's say this edge and this edge, let's say this edge. So when we choose this edge, we can say that this edge, and this edge are all covered by this one, right? So let's choose another one. We still have this uncovered and this uncovered, so we can choose this. So this means we need at least 3 vertices to cover all the edges. I'm just going to highlight them on red. So this one covers this and this, right? This one covers this, and this, and this one covers this and this. I hope that makes sense. So this is what a vertex cover is. We want to find a minimum subset of vertices that can cover all edges. A vertex cover in practice is used in telecommunications, in networking, and every other field where you require some form of connection. So we want to maximize our resources while making some form of maybe phone connection, wire connection, or even when installing security cameras. We want to make sure that we use the least amount of cameras to cover the most area as much as we can. So that's actually the idea behind vertex covers. You can, research more on the use case of this in industry. So for this diagram, we have a minimum of 3 vertex covers covering all edges. And like I said, for vertex cover, we want at least one of the vertices of connected edges to be covered. We want at least. That means it's not wrong if all vertices are covered, but we want, the keyword there is at least. We want at least one of the vertices of connected edges to be covered. So let's translate this to an LP. So for an LP, we decide what we are looking for first. So what we are looking for right now, let's express our vertex as the variable x sub v. So this will be used to express vertex, right? And for our LP problem, when we choose a given vertex, it's either represented as a 1 or as a 0. So we have 1 for when it's chosen, 0 for when it's not chosen. And what will be our objective function? Like I said, we want to find a minimum size subset of vertices. So this means that our objective function will be the minimum of these vertices. This would be our objective function. Then what would you define the constraints to be? So first of all, the first constraint would be that x is either 0 or 1. So this means that this is a 0-1 LP. And once you will have a 0-1 LP problem, the first thing I need you to start thinking about is relaxation, because 0-1 problems are really hard. So we have, and we'll be talking about hardness pretty soon in a much later topic, but I just want you to know that 0-1 problems, LP problems are hard. So once you have a 0-1 LP problem, you have to think about how to relax them, how to relax the constraints. So this is the first constraint, and the second constraint is such that the given vertices, let's say u, right, plus another vertex, would always be less than or equals 1 for each edge u and v. So this is the constraint. I hope this last constraint makes sense. Is greater than, not less than, is greater than or equals 1. That's because we want at least one vertex covering edges. We want at least one. So that means we want 1 or more than 1, right? So that's why we have greater than or equals 1. So I think the point I'm trying to make is that the pointer for greater than, cases where you have greater than or equals 1, would be where you have conditions where you're looking for greater, at least, where you're looking for at least 1, you should use greater than or equals 1. But when you're looking for at most 1, you'd be using less than or equals 1. I'll be stopping this video here. In the next one, we're talking about how to use LP to model maximum independent set problem. I would see you on the next one.